Hello and welcome to Jampro Antennas and Alan Dick Broadcast. This presentation is a workshop on the considerations for moving to a digital single-frequency network or an SFN. Firstly, we need to consider the location of your audience and how they will receive the signal. These changes depend on how you want the network and coverage to suit the situation. We will then move on to the coverage planning for a specific audience. We will also look at issues like the available RF levels within the coverage area and review the world's digital TV standards. The adjustment of various technical parameters is available according to the audience. We now move on to the primary considerations, which are how we fit multiple audiences. We will also look at the key issues and use a large-scale example of a single-frequency network project as a guide. For a traditional application, there are three main scenarios. We generally have a fixed reception scenario of a standard analog signal. In this case, we use a large tower and a high-power transmitter and antenna system. We need to deliver a high ERP or effective radiated power signal. The aim is to beam the signal to as many households as possible with fixed receivers. They will also have directional receiving Yagi antennas on their rooftops. These are common globally and provides a traditional scenario. A second scenario is where you aim to deliver the TV signal to outdoor receivers that are mobile. This scenario is generally to vehicles moving at speed. Indeed, faster than just the walking rate. Finally, the third scenario is where you are portable indoors. By this, we mean handheld devices, including smartphones and tablets. These are similar to fixed receivers as they operated in homes, but the mobile device's antennas are internal and not found on rooftops. These applications have different ways of receiving the signal. So, various RF levels are required depending on the receiver type and location. Assuming that everything else is equal, you would need to adjust the RF level if using the same transmission system. A comparison of the RF levels is needed and is a field strength planning requirement. We are using DVB-T, which is a reasonably old standard. However, the RF field is more about relativity rather than finite numbers. As a reference, if we review the UHF levels in this scenario, we have a directional antenna on a typical apartment rooftop. In this case, we had an 11 decibels gain, which is a reasonable figure. On a double-story building, the antennas will be at a height of about 10 meters or 30 feet. Typically, this is the height of a double-story building. Here, at least 56 dBm is required for a successful transmission that will guarantee the signal quality at all times. If we now look at the other scenarios, including portable indoor and outdoor reception, various things happen. Looking at the outdoor section first and assuming we are in a vehicle, it could be a car or a handset outside. However, we particularly need to focus on a vehicle as they move relatively fast. Being that we are mobile, a directional antenna is not practical. Also, the antenna's height is at that of the person holding the portable receiver. It is approximately the same in a car at 1.5 meters rather than 10 meters in a two-story house or apartment. These issues affect the total signal required for the antenna system to work. At 56 decibels, we will need an increase to at least 78 decibels to maintain the signal level. That is an increase of 22 decibels or more than 100 times. We have lost the effect of the directional rooftop receiving antenna. Moreover, the reduction in height means that trees and other buildings interfere with the signal. So you have to deliver a much higher signal level to achieve the same performance. If we now focus on the indoor reception, we still do not have the receiving antenna's directional gain. We have a low antenna height, but we now have to penetrate the building as well. The required signal varies according to the building's structure and density. However, as an approximate guideline, at least another 10 decibels is required to achieve stable building penetration. So if we compare the three scenarios to a primary analog method, the transmission to a house with a fixed directional antenna loses 30 decibels or 1,000 times less signal. With just engineering, it is practically impossible to increase the signal level 1,000 times. Moreover, a license is unlikely to allow you to, and it will be prohibitively expensive. So, we must find a method to transmit the signal. We are now lead to the various standards used around the world. Moving to a digital solution allows you to address the other two scenarios. The different digital standards worldwide include DVB-T and T2 in Europe, the Middle East, Africa, and Asia. Some countries in Asia utilize a different standard, plus a few Latin American countries called ISDBT, a Japanese lead standard. In North America, ATSC 1.0/2.0 are already in place. However, a slow transition to ATSC 3.0 is now in progress, but it is likely to take some years. There is also the Chinese standard called DMBT, which is very similar to DVB-T. We also have the ISDB-T standard operational in both Japan and the Philippines. There are other markets designated that use ISDB-TV. It has slight adjustments to the Japanese standard, which several Latin American countries have adopted. One thing to recognize is that all these digital broadcast standards use OFDM signal modulation. The standards allow single-frequency networks, SFNs, to work because the signal is robust for multicast required for a single-frequency network to work. So, what do we mean by OFDM or orthogonal frequency division multiplexing modulation parameters? Within the standard, there are many parameters that you can adjust, and there are specific parameters to be set. The parameters focus on whether you want a good signal or payload. For example, if more data bandwidth is required, the signal modulation configuration maximizes data transmission. While it does well, it's not so good at being a robust signal or coping with speed. You can also add more error correction. Then, the transmission will be more robust. It is a trade-off. You can also optimize the Doppler effect, particularly if you're trying to focus on the signal reception in a fast-moving vehicle. Moving quickly away or towards an antenna causes the received frequency to decrease or increase, distorting the signal partially. Again, you can set parameters to allow the transmission to remain more robust under these conditions. Some other parameters also affect the network coverage area, which is not an RF issue. It relates to whether the signal is working together or working apart. To explain that a little bit more, I have just shown why we look at these digital standards. So the main reason why we have developed digital standards over the years is spectral efficiency. We are looking to transmit more and more data, which means more and more programs or transmissions on the same number of frequencies. Typically, you have an 8 MHz channel for UHF TV, carrying one channel and one program with analog. We can now use the digital signal efficiencies, maybe 10 TV channels within the same bandwidth. This graph shows you different modulation sets. We have GPSK and 16 to 256 QAM. It indicates that you can change the modulation to increase the data rate. Here on the graph, you can see the data rate increase. However, to make this work, a better signal-to-noise ratio is required. The modulation that is more robust where you don't need much signal above the noise. However, your data rates become slower. As you increase the signal-to-noise, the data rates increase. It would be better to have an excellent signal-to-noise ratio. So you can select where you want to be. The graph also shows the jump between DVB-T to DVB-T2, which is the newer standard. They had better maths, brought about by better electronics. With the more complex mathematics, you need greater processing power to decode the signal in real time. So, from DVB-T to DVB-T2, computers got much faster. We could use a more complex encoding method allowing real-time encoding. The limit is within the receiving hardware, service, and IoT service near real-time data services. Traffic information or stock market information is an example. However, each of those services will use different parameters. The effect is that the coverage changes according to which service or pipeline you are viewing, which is an RF effect. You will be sending a more robust signal. So the receiver still receives the signal even though the noise level has increased, because you have a more robust signal. So, you can have different coverage areas within the same channel. So, what does this all mean with the different standards you're trying to address and the various receivers? Going back to the earlier slides, you need 1,000 times more signal to provide the multiple services. While you can adjust the parameters, you still need the larger signal. So, we can overcome this by using a single frequency network or SFN. We have a defined coverage area. Traditionally, you have one site, and do the best you can. Some places will not get covered. However, within a single frequency network, you can have multiple transmitters that all use the same frequency, hence the name of a single frequency network. However, all must be synchronized for the SFN to work. The aim is for the signals to arrive approximately at the same time at the receiver. All the signals act as one channel. They do not interfere with each other as they would in an analog environment. The key is to synchronize the signal and include overlap within specific time parameters. If the reception takes too long, then they won't work together. They will act like interference, just like an analog signal. Synchronization is handled within the SFN because they have a cyclic prefix or a guard interval. The guard interval can be made large or small. If you make it very small, you can carry more data, but you don't have much time to synchronize the signals on multiple sites. If you make it larger, you can wait longer for the different signals to be received. The result is that you reduce the data rate. So there is a balance to be achieved. This graph shows an example of 3 transmitted signals. We should assume that all are marginally different. However, each transmission tower differs in terms of distance from the receiver and the actual broadcast signal. Each arrives at a slightly different time. Here we can see the beginning of one signal and the next two. The last transmitted signal must arrive within the first signal's guard envelope as indicated. The SFN network functions by combining all 3 signals and creates a sum of all 3. If, for example, the third signal is late and outside the guard envelope of the first signal, then this will cause interference. That is what we mean when we talk about single frequency size. The settings define its scope. Should a signal venture outside of the window, then it will not work. A single frequency network has significant advantages. It efficiently utilizes the spectrum and can provide coverage for the exact area required. Also, to ensure that the signal is acceptable everywhere, we have effectively raised the signal level within a broad coverage area, avoiding a single transmission site. The total received signal strength increases with the overlapping regions, which is ideal. Moving from an area covered by one transmitter to another within the same SFN is transparent to the receiver. It does not matter which signal you receive, even if there are multiple received signals. It is effectively one signal as long as all remain synchronized. That was our introduction to SFN theory and why we wish to utilize it. We will now show you a real example of an SFN project we deployed in Singapore, where Jampro was highly involved. We installed the primary transmitter site, which is a traditional tower-based broadcast system. We also started installing gap filler sites because the client wanted a signal that would penetrate all buildings. Their focus was to cover Singapore. It is not a substantial geographic location, but it is a very dense metropolitan area. We installed the primary site, which was a high-power broadcast solution. We also installed a large tower with both antennas and transmission line. We included a combiner system that allowed 6 channel or frequencies to radiate via a single broadband antenna. We also installed a patch panel system. While all was relatively standard, the client required the signal to penetrate buildings. They were looking at installing repeater sites in an attempt to ensure that building signal penetration occurred at a suitable level. As an example of the Singapore project, this image shows a rooftop in Singapore. Here you can see the many buildings that are densely populated. It is worth noting that the apartment buildings are all the same height. Singapore is not a particularly big place, but there is more than one airport there. The Singapore Airport authorities set the local building height limits for safety reasons. The building's similar heights create a complex landscape for TV signal penetration due to the densely packed buildings. Initially, we installed 10 repeater sites. The blue dots on the map indicate the repeater site locations within Singapore. The primary site covers Singapore's central area. Initially, our client utilized omnidirectional antennas. However, these were found not to solve the coverage issues, so we replaced them with directional antennas. These refinements were part of the solution where our client needed to experiment to find the best solution. We continued to work closely with the client and supplied comparatively simple antennas. The project flexibility allowed different antenna configurations to be tried and tested using between 1 and 16 panels. We configured different antenna arrays aimed at coverage patterns for 3 different directions. Our client installed some of the antennas themselves. They defined both increases and reductions in power levels depending on the coverage area. We then worked to reconfigure the antennas as requested. The project was not a simple supply and fit but a case of testing and agreeing on the final configuration. Here is an image of the completed installation. This installation was on top of a building with a water tank surrounded by a brick wall. We mounted a pole with the antenna attached. In this case, we painted the antenna in the same color as the water tank. It blended in well with its surroundings. Other parts of the installation included both transmitters and antennas. The received rebroadcast signal comes from the primary transmitter site. The primary tower image is the left-hand tower. The translator system rebroadcasts via the local transmitters shown earlier. This image shows the GPS receivers where all signals synchronize with the GPS timing. As a further refinement, we found the antenna radiating from just one side of the building. However, the client needed coverage on both sides. Rather than buying another transmitter, Jampro supplied an additional antenna with a hybrid splitter, resulting in both sides of the tower gaining coverage. Initially, we installed 10 repeater sites, with additional sites added later to overcome the building density issue and assure the necessary signal penetration. Ultimately, 11 different project phases took place, which included testing and improving the overall coverage. Several modifications were requested, and even a complete project repurpose in some cases. Ultimately, Jampro supplied over 200 antenna systems to complete the project. These included hundreds of panels supplied over a 3-year period. This project remains one of the largest SFN broadcast networks in the world. That is the end of this workshop presentation. Thank you for watching this workshop. We hope it was useful to you. Please review our other videos and do get in touch with Jampro if you have any questions. Goodbye for now.